Hi, everyone. Thank you for showing up at 10 o'clock. You have arrived at the Commercial Heat Pump Water Heating Design and Maintenance Series. This is part 2. I am Katie from the Lighting Design Lab, and we thank you for joining us with our partners from Ecotop and DNR International. And I will hand this over to them. They've got lots of information.
Thank you, Katie. Welcome everyone back to session 2 of our commercial heat pump water heater design and maintenance. My name is Colin Grist. I am a mechanical engineer at Ecotop, a mechanical energy and plumbing engineering firm in the Seattle, Washington area. And I have been working with heat pump water heaters for the past 8 years at Ecotop. And I'm here today to dive into some of the key design considerations for these systems so that you all can be off and running quickly and in the right direction to align with the upcoming Seattle Energy Code requirements, and to just install these systems in buildings that make sense for their application to dramatically reduce the energy usage associated with domestic hot water heating. And today we have Lauren Baskar, who's going to be moderating, and she is going to be managing the questions tab or the chat. I don't know what we're using today, one of those.
Thank you, Colin. Yeah, so for the session today, you're going to need actually a couple of things to participate. And we really look forward to your participation because it makes a difference for us. It's hard to teach and to avoid. So the more questions and comments you can put into the chat feature or the question and answer tab, actually, I think it's the question and answer tab that we want here in your go-to menu bar. If you take a look at that, that'll be where you enter your questions. I'll make sure to turn my video on when I see those so that I can interface with Colin and make sure your questions get answered, and as well as your comments, if you have comments about the content today. And then the other thing you'll need is your smartphone, because we will be doing an introductory survey and an exit survey to kind of monitor your understanding and your interest in this topic. So thanks so much for all of that. Thanks, Colin.
Great, thanks, Lauren. So last week in session 1, we covered what a commercial central heat pump water heating system is, what parts make up that system, and we saw that they can vary significantly in the design from one building to the other. And it's key to match that design and configuration and the equipment with the building and the occupant you're serving. Today in session 2, we're going to look a little bit further at the details of those commercial heat pump water heating systems and determine what are the key design considerations that are really essential for success. We both want the energy efficiency savings these commercial heat pump water heating systems deliver, but we also want them to operate reliably, efficiently, and for an extended period. And so that's what we're focusing on today, is how do we design in that successful operation. And then session 3 and session 4, my colleague at Ecotop, Evan Green, is going to lead those sessions. And session 3 is really looking from the contractor's lens at these commercial heat pump water heating systems. So now that an engineer or a plumbing designer has specified a certain type of system to go in a given building, this is really addressing the installation from a contractor's perspective, purchasing that equipment, getting it to the site, and piping it together to get it up and running smoothly. And then session 4 looks at it from the maintenance personnel's perspective as well as the commissioning perspective. How do we get these systems up and running smoothly? How do we ensure the sequence of operation for these commercial heat pump water heating systems is set up correctly and working as specified? And then how do we plan in our maintenance procedures to really extend the life of these systems so that we're not creating issues for ourselves down the line? So a handful of really great sessions here, and I appreciate you all coming back to session 2 today. And I hope you'll join Evan and I for session 3 and 4 the following weeks. So we're going to start off today with a quick review of session 1. What is a commercial heat pump water heating system, and what are the components that make up that system? And so we showed this slide in session 1, and really this is here for us all to understand that we're not always talking about these large commercial heat pump water heating systems. It may be more appropriate to specify a smaller commercial system that can be located in a closet, built out of residential equipment, or maybe we're looking at multiple smaller zones in our distribution system that allows us to use smaller residential products once again, but that's serving a bigger building. We have multiple of these systems to serve one building. And so there's multiple sizes, types, and configurations that we can see in these commercial heat pump water heating systems. And today we're going to dive into some of the details on what makes sense for what application and what some of the key design criteria are, so that you can be well suited to address those with these systems and buildings you're working on. And we have a handful of available products today. We looked at some of the residential products that were introduced that are using the unitary or integrated style heat pump water heaters. And a reminder that that's the heat pump water heater packaged with the storage tank. And typically that heat pump water heater sits on top. These are most common in the residential, or most commonly sized for residential loads. But recently, A.O. Smith has released a integrated or unitary heat pump water heater that has a larger storage tank behind this heat pump unit there on the front face. Both those products use R134A, which is struggled or challenged by ambient air temperatures that drop below 40 Fahrenheit. And you'll see that 40 Fahrenheit number in the Seattle Energy Code in a few places, because the code is taking a proactive stance on addressing that certain types of equipment utilizing R134A needs to be able to heat water at those lower ambient air temperatures, but is often challenged when it's below 40. And so they address measures to make sure you have a reliable operation. And then we also learned about some single pass equipment, and this is using the refrigerant CO2 or R744. CO2 has a super low global warming potential of 1 because that's what the system is based off of, much lower than our R134 in the thousands there. And these CO2 systems primarily come in split system heat pump water heaters, where the heat pump is split off from the storage tank. However, that heat pump still has the controls needed to control it and operate that unit. We also looked at some larger commercial R134A heat pumps. Both these are manufactured in the United States and great products to specify for your buildings. These are once again using that R134A refrigerant, which is challenged by temperatures below 40 Fahrenheit. And we'll touch on some ways to address that concern in your design. So numerous available products and a variety of sizes that the manufacturers are providing, so that we can appropriately size these heat pump water heating systems for our commercial buildings. And then we also discussed the 4 components of a commercial heat pump water heating system. We have our primary heat pump water heater, which is our primary engine. This is really what's driving the system. It's taking in cool water and making it, heating it for domestic use. That primary heat pump needs to be connected to a primary hot water storage tank or tanks. And so we learned that our primary hot water storage is necessary because these heat pump water heaters are not instantaneous heaters. So we need a thermal battery, somewhere to store that hot water energy, and that's the purpose of our primary hot water storage tanks. And we also discussed the temperature maintenance system in session 1 and what it is. This is the distribution system in the building that's piping hot water to those end use fixtures. Typically, we circulate that piping to maintain the water near 120 in that entire distribution network. So we circulate it at a slow flow rate. Well, we learned that that can present issues to certain types of heat pump equipment, and it might be more reliable and more of a robust solution to separate out that temperature maintenance load with a dedicated temperature maintenance system. And so here I'm showing that temperature maintenance tank and a way to heat that tank. And this is a heat pump that's configured in a multi-pass heating cycle, whereas these primary heat pumps are typically configured in that single pass heating cycle we discussed in session 1. And then the last of our 4 components is the control system, some way to turn on and off these heat pump water heaters and any of the other equipment based on a call for heat that's typically based on the temperature sensor in the storage tank. And we learned that, we can have these custom engineered systems. That's really the do-it-yourself approach of specifying all the parts and pieces, finding a storage tank that works with a given manufacturer's heat pump and other components that go into that commercial system. And the manufacturers that have been selling these heat pumps for a while saw that there's an enormous amount of potential for getting more of these heat pump systems on the market to save a lot of energy. And so they've been developing these skid systems, which are really plug and play hot water systems, to take some of that design strain off of the design engineers. These are really proven to perform and be reliable. And so it's a great approach to talk to your manufacturer and see if they offer really a plug and play skid solution that might be appropriate for the buildings you're working on. And so we see Mitsubishi has a skid known as the Origin, and that's using a Mitsubishi heat pump and a handful of storage tanks and a electric resistance water heater configured as a swing tank. Sanco 2 also is producing the water drop. Small Planet Supply is leading this effort. And once again, this is a packaged skid solution that includes multiple heat pump water heaters connected in parallel, coupled to storage tanks that are located in these insulated closets. And then we can add another module to that to extend our heat capacity and storage volume to meet a bigger demand in our buildings. And Nile, also a manufacturer on the East Coast, they've been developing a skid system too that aligns with the Seattle Energy Code and utilizes a heat pump water heater in single pass to provide hot water to 3 storage tanks and a smaller swing tank shown there. So there's a handful of options that are coming out that are based on this really plug and play application so that we can start seeing more of the market share with these heat pump water heating systems. And like Lauren introduced, we have a Slido here today. And so this is a really great mechanism that we have to engage with you when we're in this virtual environment. And so I'll pass this over to Lauren and she can introduce it a little further.
Great, thanks so much. And Colin, I do want to say we already have a question in the chat about kind of cost effectiveness questions, so we'll get to that in a bit, but let me go ahead and introduce Slido. So you do need your smartphone. Slido is a great app, by the way. It will not track your data. It won't send you any spam. It really is just use it and then forget about it. It won't, it won't bother you anymore. So if you go to slido.com and then our event code, it will ask you for an event code. It's design all caps #2. And that's how you access this introductory survey this morning. So let's move on to the survey here, Colin, and we'll see if we can get it down here.
Yep, and there's also a QR code here so you can scan that with your phone to get to that same web page.
Awesome. So while we're waiting for folks to fill in the introductory survey, let me go ahead and ask this question from Bill. First of all, Bill is wondering if we have any case studies that highlight other building types beyond multifamily. Do you want to quickly comment on that?
We've definitely installed commercial heat pump water heating systems in other building types beyond multifamily, hotel, educational facilities, casinos, so really a wide array of building types and applications. And those systems have primarily been really efficient designs that reduce the annual energy use of the building. And it might have been the building owner's direction to lean towards that higher efficiency system, but these systems tend to have shorter than 10-year payback for new construction in our buildings, regardless, or for most building types and occupancies. The more water we use, the more savings we're going to get. So the commercial heat pump water heating systems have a typically shorter payback when we have a higher domestic hot water load, like we have in a hotel, residential, multifamily, or educational facility that has gyms and other uses of hot water.
Awesome. And then one quick question related to Seattle Code and the mandates that are coming up starting in January. Can you specify which building types are required to implement commercial heat pump water heating systems?
Sure. So it's R1 and R2 starting January 1st, 2022. And that is hotel, motel, and multifamily is my understanding.
Great, thank you.
So after the review, let us know how we're doing. Good, still processing, but ready to learn more and ask questions. That's great. Some people totally get it, fantastic. Just okay, have a lot of questions. There's still some people in that category too, so we'll try to bump you up into one of those upper tiers there. What clarification questions do you have, if any? Looks like nothing right now, but we'll happily answer these as they come in throughout the 2-hour seminar today. What topic are you most confident about? Heat pumps is definitely what most people are confident about. Market position, less confidence, primary storage, valve proposition, or value proposition, excuse me. But it looks like primarily we're most confident about those heat pump water heaters. That's great. We'll try to dive into the temperature maintenance system more today and the system design configurations to hopefully teach you a few key design criteria about those so you can be off and running and be installing these really highly efficient heat pump water heating systems. So today we're talking about what factors are essential for commercial heat pump water heating system design. And we're going to step through these, but I am arguing today that thermal stratification in our storage tanks is a big part of successful heat pump water heating systems. We want to prioritize thermal stratification in our storage tank. And what thermal stratification is essentially a hot water at a usable temperature in the majority of the storage tank at the top, a thin transitional layer of mixed water with a little bit of cool water at the bottom. And so in that design, we have a high level of thermal stratification. If we have a very mixed tank, we don't have that thermal stratification in that tank. And so we want to determine ways where we can prioritize keeping these storage tanks stratified so that the heat pump water heater can operate in a reliable and efficient point of operation. And then we're going to also talk about the configuration of the temperature maintenance system. The temperature maintenance system is definitely impacting the level of thermal stratification in our storage tanks. So we can configure those temperature maintenance systems in certain ways to address that thermal stratification so it's not an issue. And we'll walk through 2 of those configurations that have proven to be very reliable and robust designs. Then we're also going to talk about managing the distribution losses the distribution losses associated with that temperature maintenance or the hot water circulation system are driving some aspects of our design. And if we can reduce those loads, we can avoid that issue that's really driving our design associated with the level of thermal stratification in our tanks. And then the last thing we're going to discuss is system sizing. A lot of these heat pump water heaters are single speed devices. We are having variable capacity heat pumps come out, but primarily a lot of these are single speed. And so it's really critical that we're sizing appropriately and we're sizing for the actual load that the building will see. Oversizing can present issues with these commercial heat pump water heating systems. And I've seen a few of those in the field over the past 8 years, where essentially it's one large heat pump water heater treating the entire load. And there's some issues with the sizing and the cycling of that system. So we're first going to explore a case study, and this is a case study that we've used in the past in a few of these presentations, and it's the Jackson Apartments. This is a new construction building in the Seattle Central District area. So there's the building there from a 3D perspective. There's a central courtyard or walkway that connects two paths or to the street. It continues the right of way for the pedestrians. That's open to the public. It's a very inclusive building. And there's also an amazing little array of shops and retail on the ground floor to serve that community that both lives in this building and in the neighborhood around the building. This is a Runberg Architecture Group project in the Seattle area, and it has a heat pump water heating system. That heat pump water heating system is located in the underground enclosed parking structure. So up on the top right here, we have our architectural rendering of the building. We can see the west building and the east building as we're looking north in this image. And we located these heat pump water heaters in an enclosed underground parking structure that's ventilated to deal with the air temperature, to create a buffering impact or a buffering effect on that air temperature as it comes in. When this project was designed, we were specifying and utilizing R134A heat pumps manufactured by Colmac, because that was really one of the large commercially sized heat pump water heaters on the market at this time. The Mitsubishi and other heat pumps that we're going to look at later today weren't yet available. And so these Colmac heat pumps utilize R134A, which is challenged when the ambient air temperature is below 40 degrees. So we located these in an underground parking garage that is uninsulated and has a lot of ground contact to provide a buffering effect on that ambient air that comes in. So how this system operates is air is drawn through a ventilated garage door where the cars come in, and that air gets pulled down a few levels towards the heat pump water heating plant. That air is then buffered to about 40 degrees because we have a lot of ground contact, and that ground's at 50 degrees all year long. So this allows us to use those R134A commercially sized heat pump water heaters in Seattle, even when the design air temperature is around 23 or 25 degrees Fahrenheit. If we were to put these on the roof, there would be significant portions of the year where it's cooler than 40 degrees Fahrenheit outside, and so those heat pumps would not be heat pumping. They wouldn't be moving that heat into the water because it would be lower than the minimum operational temperature. So that warmed air that's now 40 degrees on our design day gets drawn in to our mechanical room on one of the lower levels of the parking garage. and that air is drawn into the heat pumps. The heat pumps take the heat out of that air. They discharge cool air back out of that mechanical room towards a garage exhaust fan system, which is sitting right about here. That's operating continuously. So that cooler air is then taken out of the building and exhausted as garage exhaust air. This allows the heat pumps once again to run all days of the year to provide heat to the system, and really increases the overall efficiency of our commercial heat pump water heating system here, because we can meet that load on those cooler days. So looking at this a little bit further, we have our conceptual schematic up top here. We have two primary heat pump water heaters and a backup electric resistance water heater, as the owner wanted a backup non-heat pump water heating system serving this building as well. And then we have three primary storage tanks, and we learned in session 1 that we can either configure those in a series arrangement or parallel. At this project, we are arranging those in series. So the hot of one, the first tank, is connected to the bottom of the second, and then the second tank is connected to the third. And this essentially stacks our tanks vertically on top of each other to really have a very high level of thermal stratification. A lot of hot water on top, a thin transitional layer, and a little bit of cool water on the bottom. And we also have a dedicated temperature maintenance system here, because this is a large multifamily building serving close to 200 units here. We provided a hot water storage tank that the hot water return from our circulation system gets dumped into, and a multi-pass heat pump water heater connected to that storage tank to reheat those losses. And so that storage tank also has an electrical element in it, meaning it's essentially an electric resistance water heater. However, that element set point is kept lower than the set point of the heat pump water heaters. So in normal operation, the multi-pass heat pump water heater comes on first to reheat those temperature maintenance losses. And then if anything happens, our backup electric resistance element comes in. Similar design approach as we have on the primary side there. So we can see here, there's one of our primary heat pumps, and on top we have ducting connecting it to the back to the parking garage, discharging that cool air out of the room. And then this is our storage tank wall. So we see we have three primary storage tanks shown there. Then there's our electric resistance temperature maintenance tank and a large expansion tank. And we also have a multi-pass heat pump water heater. And originally, this design used the last generation of Colmac heat pump water heaters, the HPA. During the construction administration phase, the manufacturer had developed and was selling a more advanced heat pump water heater, the CXA, which addressed some of the concerns we saw in the early system designs. And so we were really interested in using that more updated product. But due to the sizing of it, we switched from we had to re-evaluate what temperature maintenance heat pump we were utilizing. And this temperature maintenance heat pump, manufactured by Colmac, has a fan on a hinged face. And so we didn't want to worry about the ducting connecting to that fan with hinges for access internal to get into that unit. And so we simply located this heat pump water heater exterior to that room, so we weren't overcooling that room because it's serving that temperature maintenance load, which is fairly continuous, and so we'd be cooling that room throughout the day. This heat pump also does use 410A, so less impacted by those cooler ambient air conditions than the R134A heat pump that we're using for the primary heating load. And all in all, we're saving about 15% of the annual energy savings across the total building. So enormous amount of reduction in the annual energy use with the implementation of this commercial heat pump water heating system in the basement parking garage in place of the more common gas or electric resistance water heating system. So one of our key takeaways, I think, from this Jackson case study is that large central systems using commercial equipment can be very effectively utilized to deliver high efficiency water heating. We saw an enormous drop or reduction in the annual energy use here, and we have a measurement and verification system, so we're actually trending that data to determine how efficient the system resulted, or the resultant efficiency of this system. So I can pause for questions here, and before we go on to the next section.
And let's just give folks a little bit of time to react here. If you have any questions, that's a good time to put them in the questions bar. All right, here's one from Ian. It says, do you decide to duct cool air to the exterior dependent on the thermal mass of the garages, or is that a typical design feature now?
So let's see. Most of our designs take the cool exhaust air from the heat pump water heaters and either directly duct it out of the building or duct it at a fan system. These systems run for many hours of the day, and so if we don't duct that out, we risk overcooling an area of the garage. And so we want to ensure that there's a way to get that cool exhaust air out. Even if this garage has a lot of thermal mass, because of the number of hours these systems typically operate and the loads that they're serving, over the course of a week or even a day, you can actively cool that space if you're not discharging that air either towards the garage exhaust fan system that's pulling it out of the building or directly out of the building with ducting to the exterior.
All right, great, thank you. Here's another one. It says, why did the owner of the Jackson Apartments choose a high efficiency system? Don't the energy savings end up as savings on the tenants' energy bills?
Yeah, so the owners of this building had energy efficiency goals. They wanted to align with the 2030 district goals in Seattle. The tenants end up seeing those savings because they pay the water heating bill. But the owner team also wanted to achieve LEED Platinum here. And the heat pump water heating system is one way to essentially guarantee that amount of energy savings so that the project can achieve that really high LEED Platinum certification. And this is also being used as a marketing tool. We are very conscious about the amount of, the bills we're paying more and more as time progresses. And so the owners can market this as a more efficient building that dramatically reduces the tenant's energy bill, which saves them money. So they can put a little bit of a premium on some of those units if they decide to.
Nice. All right, those are all the questions. Thanks, Colin.
Great, we'll keep moving along. So the next thing we're going to talk about is these essential design considerations. But what I would first like to highlight to us all is that we need to understand the equipment efficiency boundaries. And so our heat pump water heating equipment may be rated by the manufacturer at a COP or a coefficient of performance, how efficient it is, of around 4.0 for a given product. But that's based on an ambient air temperature, an inlet water temperature, and an outlet water temperature. And we know that our air temperature regularly varies throughout the day and over the course of the year with the seasons. So that equipment COP isn't the best metric to evaluate the system on. We can also look at the primary plant coefficient of performance, and that's really looking at the equipment that's serving that primary system and the storage tank and the associated losses with that. And that's a great way to understand how efficient that primary heating system is. We're taking in cool water and heating it for use in the building. We want to prioritize that primary plant coefficient of performance because it's the bigger load in these buildings. There's more energy use associated with that primary water heating than, say, the temperature maintenance water heating. So we can also look at the temperature maintenance plant COP, which is essentially the equipment that's serving that temperature maintenance system and the storage tank. So this may be an electric resistance water heater configured as a swing tank, or it may be what I'm showing here is a parallel loop tank water heater with a temperature maintenance multi-pass heat pump water heater on it. So we can look at that temperature maintenance plant COP, but once again, we're not really focused on the system as a whole when we're just looking at that portion of the heating system. So what we really need to focus on is this domestic hot water system COP, also referred to as SYS COP or SCOP throughout a lot of papers, handbooks, and codes. And so the domestic hot water system COP is really looking at all the energy that's going into the system and the useful energy that's coming out of the system. And so while our equipment COP might be published by a manufacturer at a COP of 4, the domestic hot water system COP, based on the climate conditions and the entering water temperatures and how this system is configured with the backup and temperature maintenance system, that domestic system COP might be reduced to 3.0 from that 4.0 number. So we have to understand these to really address some of the issues and concerns we see with this temperature maintenance system, because this can drive that domestic system COP significantly depending on how we approach treating that hot water circulation load. And so this brings up our first key design consideration or essential design consideration, which is thermal stratification in the storage tanks. And so the importance of thermal stratification really comes down to the heat pump water heater's heating cycle. Single pass heat pump water heaters are super efficient at taking cold water in and making it hot. This is a reliable point for them to operate at. Once again, the heat pump is operating in a heating cycle, and so this is a very reliable point for that heating cycle to be operated and tuned to. And we send this hot water out through the mixing valve, which is often taking 140-degree water in our storage tanks, tempering it down to 120-degree water going out to those end-use fixtures with some amount of cold water to get that tempering effect. But as we circulate that hot water in the distribution piping, we, in some cases, return that hot water to our storage tank. And over the course of a night, or a period of low use in the middle of the day, that water mixes and de-stratifies our tank. Because it's a continuous operation, it's pushing warm water in, which is pushing hot water out the top of our tank. And over time, that's going to create this big mixed layer for our single pass heat pump water heater. So when that single pass heat pump water heater turns on, we start to pull in water that may be at 110 degrees Fahrenheit. So it's already heated most of the way, and we're trying to find or finish heating it or put more heat into it. And because it's already hot and we're trying to dump heat into it, that can be a very challenging operational point for that heat pump water heater, and it may result in issues. The other thing to consider here is how this system was sized. If we have a very well stratified tank, we're using our storage volume very effectively. We have a lot of hot water at usable temperature at the top of that tank. So we can discharge that to the building while the heat pump runs in the background, keeping that tank charged. But as we pipe that return water into our storage tank, we reduce the effective storage volume of that tank, because now there's less of that water that's at usable temperature or above usable temperature, and a significant portion of it can be below usable temperature, often at around 110 or 115, depending on the temperature that's circulated in the hot water circulation system. So that destratification both reduces the efficiency of our heat pump water heater, it reduces the efficiency of our storage tanks, and can present operational issues or points which are very unstable to operate our heat pump water heaters at. So this is one of the primary design issues with early heat pump water heating technology, and is still a design issue today that we need to address primarily through design and configurations of these heat pump water heating systems. So here's our temperature maintenance system again. We saw this in session 1, and so just reminding us all that that temperature maintenance system is keeping that water in the distribution system hot. And that system is actually a pretty substantial portion of the total energy end use. So here's our pie of the annual energy end uses for a multifamily building. And we can see that that temperature maintenance system is 10% of the total annual energy. And it can be about, 30 to 40% of the water heating energy. So it's a fairly substantial load over the course of a year, even though it's just a trickle of warmish water back into our storage tanks. So we want to prioritize our system COP, and piping this in a dedicated arrangement, as I'm showing here today, we can prioritize that primary storage tank or that primary system COP and come up with a clever design solution to increase our temperature maintenance COP. So the temperature maintenance system, what's included, once again, this is a slide from session 1 that's really is just to remind us about this system, and that it's the hot water piping that's distributing that water through the building. It's that mixing valve, that circulation pump, and some way to reheat those losses. So we still have a temperature maintenance system with our gas or electric resistance water heating systems, but they're not challenged by that return water temperature like the heat pump, the single pass heat pumps are. And so here with the heat pump example, we might be looking at a dedicated temperature maintenance system to address those issues and the thermal stratification. So I'll pause for questions here before we jump in to some design considerations or configurations that work well to address that temperature maintenance load, and a discussion on how big that temperature maintenance load can be.
Great, and just as a review for everybody, to remind you that the web recording and the PDFs of this presentation is available, or will be available, on the Lighting Design Lab website just a few days after following this presentation. So just so everybody knows. I don't have any technical questions in the chat at this time, but I do want to just pause and let people maybe finish typing or thinking. It's a lot of technical material in this session. So, Colin, I have to tell you, I'm getting better at these temperature maintenance system configurations. The more times I moderate for you, I'm starting to pick up on all this stuff.
Right. Yeah, it's something that, when I first started working with these heat pump systems, I was completely unaware of this and the concern. But at Ecositer, we learned through a few of our buildings that we've worked on that this is a big load, and it can be a big issue for these commercial heat pump water heating systems. And so I'm happy to share as many of those lessons learned with you all today, so that you don't have to go through that learning exercise in the field.
Here's a good comment from Jack. It seems like the potential Achilles heel of the system could be this, right? The temperature maintenance system. Could you say more about what study you've done about the options for the mixing valve? It seems like you would not need much temperature maintenance if the mixing valve was managed intelligently.
So the mixing valve, managing, I would say we manage it intelligently already. But the temperature maintenance, the issue is how large is this distribution piping and how uninsulated is it, or what's the level of insulation? We have a lot of distribution piping and very little insulation. We're going to see a big temperature loss or a high flow rate, and that temperature loss and flow rate will de-stratify our tanks, and so that's where we really have the Achilles heel. If we have a very short distribution system that's super insulated, we're not going to see that level of temperature loss, and we're going to see the circulation pump operating very slowly, or much slower than if we had a large distribution system. So in that case, it's less of the Achilles heel, but it's still something to be aware of when you're designing these systems. But yeah, absolutely great note. It pretty much is the Achilles heel. It definitely was for a lot of the early designs.
All right, Colin, and that's the end of the questions. Thank you.
Great. So now we're going to talk about the configuration of the temperature maintenance system. And I highlighted this a little bit just a minute ago, but the first thing to understand and to work with your plumbing designer is, what is this hot water distribution system going to look like? Is it a single family home where we have a solar thermal hot water system here? We could pretend that's a heat pump for this analysis on the roof. It's connected to a storage tank and a pretty short section of distribution piping. Even if this piping was circulated, we're not going to see a substantial temperature maintenance load in that arrangement, just because we don't have that much piping in the building, and it's probably going to be 1/2 inch or maybe 3/4 inch piping. When we start to stack multiple single family homes on top of each other, like we do in a multifamily building, so these gray boxes each represent a multifamily unit, we start to increase that distribution system. So now if we have a central hot water plant, regardless of what it is, if it's a heat pump or a gas water heater, we might now have a 3-inch or a 4-inch main carrying hot water down level 1 of the corridor, and then risers that go up to serve multiple units are connected on top with another maybe 1.5-inch hot water circulation main, and then that's piped back down to our, I guess it's going down there, back down to our central heat plant. So if we have this large distribution network, we're likely going to see higher temperature maintenance losses, which will have more of an impact on that single pass heat pump water heating equipment or our system overall. So the first thing that I always ask myself when I'm working on a new product or project is, what is this distribution system going to look like? And that's going to lead me to a few different design approaches to address that concern with the warm circulation water returning to our primary storage. And so we have 4 systems or options we're going to talk about today. We have the dedicated parallel system, which is our Jackson Apartments example, as well as a few others. We had our dedicated series. We have our dedicated series example, which is the swing tank concept. And both of these are called out for in the Seattle Energy Code under the system design section, which is C404.2.3 something, I think 0.3 maybe. So these are great options for dedicated systems, or essentially a dedicated temperature maintenance system, to separate that primary and the temperature maintenance load to address the thermal stratification. And so we'll step through those both together. We can also essentially have a combined system, which is more of our common approach right now, where we have the hot water circulation going back to the storage tank We don't have a dedicated temperature maintenance storage tank or a dedicated temperature maintenance heater. All of that's combined. And so arguably the primary heat pumps are reheating that temperature maintenance load. This would be more appropriate for a multi-pass heat pump water heating system, and we'll discuss why in a little bit. And then the last one is no recirculation. This is less common in these large multifamily buildings, primarily because of access, first cost, and the resultant less efficient system. But essentially we can put a heat tape or a trace on the entire hot water distribution network that keeps that hot water piping around 120 degrees. This is a common product to prevent freeze protection, where it's keeping that water in the piping above 40 degrees. And so they also sell a very similar product that keeps it at a higher temperature, closer to that 120 degree value. So the first system we're going to look at is our dedicated parallel example. And once again, this is what the system we have at Jackson Apartments that we just stepped through. But what we have here is single pass primary heat pump water heaters to maximize the efficiency of those primary heat pump water heaters and their heating cycle. Then we have a primary storage tank that's coupled right to that. So as cold water comes in, that cold water hits that temperature sensor, controls the heat pumps on. The heat pumps start drawing in that cool water and putting hot water towards the top of that storage tank. Then as people use water in their apartments at their fixtures, hot water is drawn out of that storage tank and feeds to the hot side of the mixing valve and goes out after being tempered with cold water and the return circulation water. And we have a dedicated system, so we can draw essentially a line down the middle of our page, and the temperature maintenance system's on half and the primaries on the other half. And so that temperature maintenance system, we have a circulation pump, which is moving hot water continuously through that distribution network or nearly continuously. And that water is being dumped into the bottom of the temperature maintenance storage tank. And some of it is mixing on the cool side of the mixing valve with cool water. Then that temperature maintenance heat pump water heater gets a control signal and is configured in multi-pass. So it's trying to put as much heat into that water for a given cycle. The water or the entering water flow rate is unmodulated. It's just trying to dump as much as possible, typically raising that water about 10 degrees Fahrenheit through each pass of that heat pump. And so that keeps or reheats that 110 degree warm return water back up to 120, and then it starts pulling in 125, heating that up to 135 towards the end of its cycle, so that then we're mixing hot water out at about the same temperature as we're storing in our primary storage, so that this is a consistent temperature on the hot side of that mixing valve. And so these systems really work in parallel together, and we can look at that piping connection as it's connected to the top or the outlet side of our temperature maintenance tank there. This is a great design approach for systems that have a very large distribution network or hot water distribution system, because we can appropriately size this temperature maintenance multi-pass heat pump water heater for that application, so that the cycling of this unit is appropriate. We're not doing a bunch of short cycles, and we can also reheat this water fairly efficiently. This heat pump water heater will probably be operating in Seattle, depending on its technology. If it's R134, maybe a COP of 2.0 to 2.5. And so that can be much more efficient than our electric resistance water heaters, which are going to be operating closer to a COP of 1. So once again, this parallel example with the dedicated multi-pass heat pump is a great option for these larger commercial multifamily buildings or larger buildings with significant domestic hot water circulation systems. that results in a higher temperature maintenance circulation load. So we can look at one of these or another one of these projects. This is from Yesler 2, which is the Cypress Apartments in the Yesler redevelopment area. And we have 2 primary heat pumps. There's one shown there, and there's actually a second one back in that corner of the mechanical room. And we have a temperature maintenance heat pump. And that temperature maintenance heat pump sure does look a lot like our primary heat pump water heater. The one difference is that this primary heat pump water heater is configured in a single pass heating cycle. So the entering water to that unit is modulated. It's increased and reduced to always discharge a set water temperature at 140 degrees into our primary storage tanks. This temperature maintenance heat pump water heater isn't controlling to that entering water flow rate. And so we're just trying to dump as much heat into that water as possible. And that water is already fairly warm. So typically high flow rates, entering water and leaving water flow rates through this multi-pass heat pump water heater with a much lower lift. And even though this is essentially the same product, we can configure that cycle in the single pass heat pump water heater or the single pass cycle to treat our primary load and the multi-pass to treat our temperature maintenance. And we have our primary storage tank. This is where we're storing that hot water. And at Cypress, we have 5 storage tanks connected in series. So we have our cool tank, and then they get hotter as we go to the left. So during normal operation, all of these tanks are charged. There's hot water all the way back to this second one, right, or to the first one right above that temperature sensor. And then as cool water comes into this, that's going to result in that temperature sensor dropping, which is going to turn on the heat pumps, and we're going to start to recharge these tanks while hot water is going out to the building from our hot tank at the end. And we do have a dedicated temperature maintenance system, like I mentioned. So this heat pump in multi-pass heating cycle is configured or connected to this temperature maintenance storage tank, shown in that conceptual diagram one slide earlier. And then our mixing valve here is a larger mixing valve due to the size of this building, and that's mixing the water out to the occupants so that we can always deliver 120-degree water even when we're storing water at higher temperatures in our storage tanks, as well as our temperature maintenance storage tank. This is a really great, proven, reliable and robust design with these larger multifamily buildings. We do have a piece of equipment that may be new or extra, but if we look at this system sizing as a whole, this heat capacity would have been in the primary heat pumps if we would have returned to primary, except we would have resulted in a lower efficiency of those primary heat pumps. So we would have had to increase the amount of them to address that lower efficiency. So this is really a great way to really match these heat pumps to the load to get the most bang for your buck out of these, or when you're working with a larger commercial building with a large distribution piping network. And we're also going to look at the dedicated series system. So this is a primary heat pump with a in-series swing tank or electric resistance water heater. And this, I'll pause for questions maybe if Lauren's got a few queued up.
Yeah, thank you so much. Yeah, it's good, I think, to pause after each one of these configurations. So let's start with Doug's question. For the single pass primary heat pump water heating system with parallel temperature maintenance, number 1, why does the cold water not go directly to the heat pumps instead of entering the bottom of the tank first?
Great question. So that gentleman is talking about this cool water pipe that's going into the storage tank, and then there's a cool water pipe that's going from our storage tank to our heat pump. We could also theoretically, we could connect this cool water pipe right here so that it can go into this storage tank or be pulled that way. We've done that in the past, and it can work totally fine. The one issue is with this design, we have a way to buffer so that cold water enters and then some amount of mixing happens at the bottom of this tank, even if we have a very good stratification, so that we have a steady entering water temperature out to this heat pump water heater. If we tee that cold water in and this heat pump water heater is towards the end of its heating cycle, it's going to be pulling water that's closer to maybe 90 to 110 degrees into that heat pump right at the end of its heating cycle. So if we connected a cold water pipe here and we had a significant hot water load, we'd essentially end up pulling a bunch of really cool water into that heat pump water heater. So the unit would be drawing 100-degree water, and then all of a sudden it's drawing 50-degree water from our city water connection. That change can shock the heat pump. And so it's a more appropriate design approach to mix it in first. However, we've done numerous projects where it's essentially connected on this end. Most technologies can deal with it fine, but some of the early generations of heat pumps would result in system errors or a system restart required because of that shock in change of temperature of the entering water temperature on that cold side.
Great, thanks, Colin. Here's another question too related. Does the mixing valve, especially looking at this diagram, this is a great diagram for this, does the mixing valve have 3 inputs and 1 outlet? And is this an off-the-shelf component?
Yeah, so this is a common way to pipe a mixing valve regardless of whether it's a heat pump or a gas water heating system, where we take the return water from our circulation, put it to the cold side, also take our city water connection and put it to the cold side. Those are typically connected together right before the mixing valve so that there's only 3 connections on this mixing valve, and these 2 are teed together right before that cool water connection.
Mm-hmm. And this is an off-the-shelf component?
It is an off-the-shelf component.
Okay. We had another question related to that. Is there a particular logic to getting the right temperature with the most efficient approach with that mixing valve? It seems as if it weren't controlled properly, it might result in inefficient operation or scalding or other things, right, that could happen with residents.
Right. So we're storing water often at 140 degrees in these storage tanks. And so we want that water to go out at 120. At 140 degrees, it takes, I think, maybe 5 to 30 seconds to scald someone. At 150 degrees, it's only a second or 2 to scald someone. So we do have a concern with scalding, especially in our more sensitive occupancies like senior or young children in a school, right? We don't want to scald those folks, and they have slower response times. So it's important to accurately size this mixing valve so that it can mix to those flow rates, because what we've seen is if this is oversized or undersized, however most designers are oversizing this, that it has good control over the discharge water temperature, the mixed outlet water temperature, when there's a high flow rate, so when there's a lot of use. But when there's little use, it has not as great of control over those lower flow rates. And so it's good practice to specify parallel valves for our larger buildings, because then we can get good control over both the high and the low flow rates that we see during normal operation. It's also beneficial, at least from what I've seen, is to use electronic thermostatic mixing valve. So thermostatic is going to create a static temperature out. It's the goal. And electronics mixing valves are typically just faster to respond than paraffin wax or bellows or other more common historical mixing valves. Is those paraffin wax, they're relying on a medium to expand to close off essentially one side of the piping. And that electronic mixing valve is essentially using a solenoid valve to shut down or open up to control that flow rate. So there's a quicker response with that electronic operation.
Awesome. Colin, last question. What kinds of problems result from heat loss in the stratified primary storage tank?
Yeah, so great question. So if we oversize this a ton, like if this is 3 times the capacity that we need, and we have a normal day of operation, we might not flow water through this entire tank or result in a changeover, essentially, like new water in this tank over the course of the day. So that's why sizing is really one of the really key design considerations that we're going to discuss on next, because if we're not cycling water appropriately through this tank, we can essentially have this tank drift down in temperature. So this once 140-degree water is now 120 because there just hasn't been that much use and it's oversized initially. So sizing is really critical. And then the other critical aspect that we can do to provide a little bit more of a robust design solution is actually take this hot water and get a little bit of an advanced temperature maintenance storage tank and discharge it right in the top, so that there's some buffering effect there of if this water loses a little bit of temperature, we can heat it back up there. If we take this hot water and put it at the bottom of our storage tank, like we do in a swing tank example, then we risk this multi-pass heat pump water heater pulling in water that's already at 140 degrees Fahrenheit, which would create issues and be a problematic operational point for that unit. So we can take this pipe and tee it in right at the top, but we don't want to take it low into that tank. We just want to use a little bit of this volume on the top to provide that buffer.
Great. All right, Colin, we're through with questions. Thank you.
Great, moving on. So the next system we're going to talk about is once again a dedicated system where we separated our temperature maintenance and our primary heating loads. And this is the series swing tank system. So here, once again, we have single pass primary heat pump water heaters that are taking cool water in, moving heat into that water and storing it at the top of our storage tank. Then when there's a load or demand for hot water in the building, hot water comes out of that primary storage tank, and you'll notice that it goes to the bottom of our temperature maintenance swing tank. That effectively takes this overheated water, 140 to 150 degrees, and mixes it with this water, which is returning at a lower temperature because we're circulating, so typically 110 to 115. So if we have periodic use, we can transfer enough energy through this overheated water to essentially offset the losses in our temperature maintenance system to prevent this electrical element from running. And that's really the goal with this swing tank system, is how do we keep this electrical element off? And we're doing it by transferring overheated water from our primary storage into the bottom of our temperature maintenance tank, which then is not stratified and is very mixed, is the intent. And so we're mixing those two streams together and keeping this water in general above about 125 degrees Fahrenheit. Then if we have a period of no water use out here, so no one's using water, this is 4 to 6 hours overnight, we're not going to be transferring that overheated energy. No longer happening, right? No one's using water. So then that's when this electrical element comes on to maintain the water at 120 or 125 in this temperature maintenance storage tank. The volume of this tank, how big it is directly associated with how many hours of the no use period we can coast through. So if we have a very large volume, we can coast through a longer no use duration. If we have a very small volume, we're not going to be able to coast through much of that no use duration. So we want to appropriately size the volume of the storage tank to be large enough that we can swing the temperature in this tank from 140 down to 125 during our low use period. And then water comes back in, and or overheated water comes back in and starts to charge this storage tank again once we have use. So the amount of water people use and the periodic use of that can be a very effective way to offset these circulation losses if we overheat that water and pipe it as I'm showing here. And this design is really, really appropriate for CO2 or R744 heat pump water heaters, because those heat pump water heaters can only be configured in a single pass heating cycle. Those heat pump water heaters are also super efficient at making overheated water. So we can heat water up to 150 degrees Fahrenheit and be at a very similar efficiency than if we were heating it to 135 or 140 degrees Fahrenheit. On the other hand, R134A heat pumps like the Colmac, they're less efficient at overheating that water. So we're going to see a significant reduction in our primary COP with R134A heat pumps when we're trying to heat that water up to 150. So this swing tank example, or the swing tank system configuration, is more appropriate for CO2 or R744 heat pumps and less appropriate for 410A or R134A heat pump water heaters, because we're trying to efficiently overheat this water and then transfer it. And the benefit too of R134A and 410A is we have the flexibility to connect them in single pass or multi-pass. So we have that option to have a multi-pass heat pump water heater from the same manufacturer that's providing our single pass heat pump water heater. So once again, in the series swing tank example, we can essentially draw a line down the center of the page and keep the cold water on one side and the hot or the return circulation water on the other. And so we have two dedicated systems. We have something that's addressing the temperature maintenance load, and we have something that's addressing the primary load. And these two systems work in series, as I'm showing here with this pipe connection from the top of our primary to the bottom of our temperature maintenance. So buildings that have small distribution systems with very insulated piping, you might be looking at Sandin or Sandco 2, same product, just a name change recently, or the Mitsubishi product, or another CO2 heat pump that can really heat that water efficiently to that higher temperature. Because the higher the temperature in the primary storage, the more energy we can transfer into that temperature maintenance tank, the more load we can offset then from that temperature maintenance heating system or temperature maintenance losses. So one of the first projects that we implemented this on was a retrofit of the Elizabeth James house. And this is a senior low-income building serving about 60 apartments in the Seattle area. And we utilized 4 Sandin heat pump water heaters that are all connected in parallel. Then there's cool water and a hot water main that are taken inside the building down here into this mechanical room. So they're coming through this wall right in the top left corner of this image here. And so those pipes are then connected to this primary storage, and we can see the hot from our primary storage goes up and out and connects to the bottom of our temperature maintenance swing tank. And then we have our our temperature maintenance return, hot water circulation return coming down and also connecting to the bottom of that temperature maintenance swing tank. So at this project, we reused the current electric resistance instantaneous water heaters, which there's 3 of them. There's one there, second one there, and third one there. Hard to see behind those storage tanks. So those are connected to this temperature maintenance swing tank, and that's essentially putting those elements in the tank. So we have an electric resistance water heater with those instantaneous electric heaters on this temperature maintenance tank. And this has been a very, very successfully operating system. It allows these to operate in a reliable and efficient mode, not push them outside their heating cycle boundaries. And because of this building, it has a relatively small distribution network, and the piping's relatively well insulated for its age. We can actually offset about 90 to 95% of those temperature maintenance losses with the primary energy that we're transferring over. So really highly efficient system because we're preventing these electric resistance instantaneous heaters from running with this swing tank design approach. And here we also have an electronic thermostatic mixing valve. And primarily that's because we want that quicker response time and that more accurate control. Because the hot side of this mixing valve, the water coming out of this hot water pipe, when this storage tank, the temperature maintenance tank is fully charged, it's going to be at 140 degrees Fahrenheit because we're transferring 150 degree water into it and we're still mixing some water. Then in the early hours of the morning, it's going to have swung down in temperature closer to 125 degrees in the storage tank. And so now we went from 150 to 125 on the hot side of this mixing valve, or excuse me, 140 to 125. And so it's really important that we have good control over those outlet water temperatures, mixed outlet water temperatures, so we're not scalding these senior occupants.
Quick question, Colin, about the piping and the sizing here. It says, what is the pipe sizing on these apartments for the exterior piping? It looks like they're super insulated.
Yeah, so out here, we actually have 2 inches of insulation on this pipe, and it's a 3/4 inch pipe that then step down to 1/2 inch connections to go to these sand-in units. So we have about 2 inches of insulation and then a metal jacket to prevent birds and other critters from damaging that.
Great.
And this is one way to really address freeze protection, because we now have these heat pumps outside. Seattle gets cold. It snowed 16 inches up here in North Seattle a year ago, and we need to protect those from freezing. And so we can insulate them with a little bit of extra insulation, and the periodic use is enough to keep those above freezing temperatures and prevent us from putting a freeze protection heat trace tape product on those piping legs. So pausing for questions here to discuss in any more detail or depth of these 2 dedicated piping configurations. We got the in-series swing tank and the parallel with the multi-pass heat pump water heater. Is really great options to allow the primary single pass heat pumps to operate in a very reliable and efficient mode of operation.
Yeah, and I'm just pausing with you, Colin, to see if there's any, if there are any questions that come through, trying to give folks time to type. That's always the piece.
Absolutely. So in-series swing tank, think CO2. And one of the first steps you should do is minimize the distribution losses, because the amount of energy you can transfer is directly correlated to the amount of use in your building. So you want to minimize those distribution losses so that you can reheat close to 100% with that transfer of energy from your primary system.
So here's a question. When you have multiple primary tanks, are they always in series?
So for single pass equipment, they are typically, if not always, in series. For multi-pass equipment, multi-pass primary heat pump water heaters, you may and likely will want to connect those in parallel. And also your hot water discharging from a multi-pass heat pump water heater is typically not at the top of the storage tank. It's lower down, because during the multi-pass operation, we first start at taking we first start with 50-degree water, we heat it up to 60. And so we want to put it low in the storage tank, because if we put that 60-degree water up there, we're just going to have cool water up here going out to our occupants. So typically this single pass heat pumps, multiple storage tanks are connected in series, and they can be connected in parallel, but you often get a little bit better use out of your tanks if they're connected in series, and the control is slightly simpler if they're in series. And then multi-pass heat pumps, there is likely reason to connect those in parallel if you have multiple tanks.
All right. No other questions. Thanks,
Great.
Colin.
And both these are once again called out in the Seattle Energy Code under the system design section, C404.2.3. And there's probably another number or two. And the last, or the third system we're going to talk about is the combined system. And so our primary and temperature maintenance systems are combined. We don't have a dedicated system here. This is what's most common in probably most of the buildings out there today that have a central domestic water heating system. So this is the all eggs in one basket approach, or both primary and maintenance loads are done by one system. There's some issues with this, and they primarily result in cycling and sizing first, or we have some risks associated with cycling and sizing. So the hot water circulation load is nearly consistent, or consistent 24 hours a day, 7 days a week, 365 days a year. And this is a fairly low loss rate, but because of the hours it operates throughout the course of a year, it ends up being a big overall load. So low losses, but it's always happening, so it adds up over time, and so it's a fairly substantial load over the course of a year. But if we look at it over the course of an hour, it's a very small load compared to our primary load. So actually taking that hot water and making it hot for use. And so there's a sizing scale issue there. Is we might have this hot water load be 2 to 3 times more in scale than this return water load for our 100-unit building. So we have to be aware of that when sizing, because if we're sizing for our primary load, which is 3 times larger than this, we might, and we're sizing for the design day condition where it's coldest outside and it's the coldest water that we're treating or that we're heating up, we might have a very oversized heat pump to treat this return water. And so that would result in frequent cycling. And because these heat pumps are, operate in a heating cycle, that frequent cycling on off over the course of an hour can create substantial issues and reduce the longevity of this type of equipment. And so those cycling and sizing issues are a real concern, and it comes down to the scale difference between the hot water load and the temperature maintenance task or load. It also, the return water, we take it back to our storage tank, it's going to mix this volume of water to some extent. And so it's essentially going to lower our effective storage volume because we have less usable water on top. And that's going to mean we're just going to have to buy more storage tanks to meet a given load in the building. And we also have to control those heat pumps a little bit differently to address that lower effective storage volume, which likely and often does operate or result in a lower heat pump water heater coefficient of performance. Because now we have to turn on these heat pumps earlier or when the water's warmer in the tank, and so they're heating more of that warm water during their normal operation. So this is why the combined, or those are some of the risks with that combined system using a single pass heat pump water heater. Now you can use a multi-pass heat pump water heater to address some of those concerns, but it's really important that you still pay attention to these risks highlighted on or noted on the screen. Because a multi-pass heat pump water heater, once again, if we just have one unit, the amount of heat capacity needed to meet the primary load is 3 times greater than the amount of heat capacity needed to meet the return temperature maintenance circulation load. And so you need to design in staging or have a variable capacity heat pump device. And there aren't that many of those out there. And so you want to have, instead of one large heat pump water heater, you might want to have 2 to 4 smaller heat pump water heaters that can be staged on, so that one heat pump water heater can run at that lower capacity to meet and reheat that temperature maintenance loss, and then the others can come on to meet that higher demand, that bigger load that's associated with our primary heating task. And then the last risk is, this is really technology dependent. Our CO2 single pass heat pump water heaters are going to be really impacted, their coefficient of performance, by that warmer entering water temperature. So probably not a great application for this. Our R134 or 410A multi-pass heat pump water heaters are going to be more appropriately, their heating cycle will be more appropriately tuned to deal with it. So less of an issue, and those are the technologies that we'd be leaning towards with this type of design approach. But all in all, whenever I do a sizing analysis, the first cost of the equipment tends to be about the same if we're doing a dedicated parallel system with a multipass or a combined system like I'm showing here. And it really comes down to how we're reducing the effective storage volume of that battery bank or our tank, and the lower COP, which means less heat into that water over a given time period. So possible, I believe the Seattle Energy Code requires a multi-pass heat pump water heater for this design configuration I'm showing on the screen. And if you choose to go down that route, please just be conscious about the sizing, the cycling, the lower storage volume, and what technology and refrigerant you're utilizing. And I can pause for questions there, or we can go through the last system, which is the heat tape or trace. And this isn't that common in our industry, but we're noting it here because it is an option in the code and can maintain temperature in that distribution network.
Quick question here from Ian. If you have a combined system with multiple tanks, would they be in parallel with recirculation water distributed or with tanks in series?
Yeah, that's a great question. So when we have multiple tanks and they're parallel, balancing through those tanks is really, really critical. And I noted that in session 1, because otherwise we can have a tank that drifts in temperature away from the other tanks in our parallel group. So we have to be aware of that. With a multi-pass heat pump in this combined system, yes, you'd be leaning towards that parallel tank design. And then that hot water circulation needs to be balanced across all those tanks, as well as the cold water and hot water flow out, and the heat pump entering water and leaving water flow. So now instead of one flow rate to balance across a group of tanks, we have 3 different flow paths to balance across that group of tanks. We have the cold water going in and the hot water going out that need to be balanced. We have the entering water to the heat pump and the leaving water from the heat pump that needs to be balanced. And we have the hot water circulation return in and the hot water out that need to be balanced. And so you want to address that through equal distance piping with that parallel tank design, and then add some kind of control valve to the entering water connections to those tanks so that you can fine tune that equal distance piping. But balancing valves to get balancing across multiple tanks alone is not typically adequate enough to maintain a good balanced tank arrangement, because we see flow rates vary from 1 GPM to 10 to 30 GPM, and those valves will only be balanced to a given kind of or smaller flow range than that large flow range we typically see. It's a great question from Ian. Thanks for all those, and keep them coming. So heat tape or heat trace, this is relatively uncommon because we have these larger distribution systems. But if you're maybe serving 3 to 4 units and you have access to that hot water piping that's serving those 3 to 4 units, this may be a really low first cost option, but will result in pretty poor performance because this electric resistance heat tracer tape is operating at a COP of 1 or less than 1, whereas our heat pumps or our swing tank is operating at a COP of closer to 2 or above if we're sizing that swing tank appropriately and we're having multi-pass heat pump on that dedicated parallel example. This is an image I just pulled from the web, but it shows essentially what I'm talking about here. Before, hopefully someone insulated this. This is likely heat tracer tape for freeze protection, as it looks like we're outside here, maybe on a rooftop. But essentially the distribution piping would be wrapped, or a red heat tape product would be connected to that distribution piping, and then we'd have insulation around that. And that product is designed to keep that water or that pipe at 120 degrees or close to that temperature. It's electric resistance, so not that efficient. It does have some access and some serviceability requirements. So for our larger buildings, it's typically cost prohibitive, and we want to be pushing towards those more efficient solutions like the combined system, if we address those risks I noticed, or one of the dedicated systems we highlighted earlier. And pausing for questions here before we move on to the next section, which is a discussion on managing and reducing the distribution losses associated with that temperature maintenance system.
Colin, there's no questions in the chat, so I say go ahead.
Great. So we all know about recycling in the United States, but there's actually 3 steps to recycling. First, we reduce, then we reuse, and then we recycle. And I think a lot of us in this fast-paced American society just go to the recycling stage. But I'm arguing that even for recycling or anything, is we want to reduce first. Before we address this problem, we want to make this problem as small as possible. And so we can do that by looking, of course, at the weak links in our chain. And one of those weak links for these distribution systems is the pipe clamps and supports. These are required to be thermally broken in the Seattle Energy Code when the pipe's traveling horizontally. However, not common practice from what I've experienced commissioning various projects, and it's typically pretty costly to add it off after the fact, even though it's it's code required and we should all be doing it. So this is a thermal image, or actually a regular image from a hot water pipe in a garage. and then a thermal image of that same pipe. And the clamp support can be seen here. And so if we look at this really good example of a fully thermally broken pipe clamp support, this is in a garage, so it's cool. We can see that the purple
Okay, let's see if Colin comes back. Yeah, I see him too. Let's hang on here and see if Colin's internet gets restored. Sometimes we have these disconnection problems. Let's pause and see. So let me work with Colin on the back end to get everybody to get Colin up to speed, and we'll be right back. Hang on, everybody. All right, everybody. It looks like Colin's computer suddenly rebooted and he's restarted on him. So he'll be right on again. He's rebooting and he'll be back on soon. So it's a good time for a coffee break and we'll be back in. I'd say let's give us another 3 or 4 minutes. Grab some coffee and we'll be right back with you. Thank you. All right, everybody, still waiting for Colin to come on back. Here's what I'd like to do, though, is to send you through the chat the link to the Ecosizer tool, which Colin will be showcasing here in just a bit. And it'll give you an opportunity to kind of go play with that. It's a free online tool. You can take a look at it, try configuring your own or sizing your own system there. So I'm going to put it here in the chat for you. Here's the link. And take a look. See if you can play with that for a bit, and we'll get Colin back online here in just a little bit. All right, thanks for your patience. Bye-bye.
Sorry about that, everyone. Don't know what happened, but my computer just shut down on me, so really apologize. I'm gonna try to keep my video off for the remainder, see if that helps with the bandwidth, but it didn't seem to be on the internet side, so we'll see if that helps at all. Lauren, can you see my screen again?
Yeah, and we didn't have any bandwidth issues for you at all. You were clear as a bell, and video was just fine. So I'm thinking it might have just been either lost internet connection or something like that.
Yeah, computer did a full reboot, which is exciting during the middle of a presentation. So once again, I apologize, but we'll keep progressing here. So we're talking about the distribution system, and we really want to drive down the losses first. We can do that with better pipe clamp supports that's aligning with the Seattle Energy Code. Here's an example of one of those thermally broken pipe clamps, and it really works. We can see that this is in the garage. It's connected to the garage up here, or the garage structure. And we see that as 50 degrees, but we don't see that temperature bleeding in or the hot water temperature bleeding out to this pipe clamp support, as we note that the hotter temperatures are these whiter or yellow colors. So these are regularly available. They're standard products. It actually reduces the amount of time the plumbing insulators have to be present on the scene, which typically reduce first costs as the plumbing contractors install the piping with this certain pipe clamp support, and then the insulators can come back and just insulate up to that support rather than working around it, which was typically how it's been done in the past. The other really, really great way to both reduce first cost and to drive down the temperature maintenance losses is to size the plumbing distribution systems with a more appropriate sizing tool than Appendix A or Appendix A plus C. These are all UPC methods to size our hot and cold water systems. And just looking at this from a case study in Seattle for a 100-unit apartment building, I put a little summary table up here. Appendix A is going to require or assume that the peak flow rate is going to be 260 gallons per minute, and we need a 4-inch cold water main to meet that high flow rate. So our hot water main would also likely be around that same size. 4-inch pipe is fairly expensive. Appendix A plus C, that takes in the bathroom groups and various usages, and that's going to reduce that peak flow rate from 260 to 205 gallons per minute, which still requires a 3.5-inch main. So the city might just put in a 4-inch main there regardless of that slight reduction in sizing. Appendix M is the peak water demand calculator. It's new in the 2018 Universal Plumbing Code, and it's going to result in a peak flow rate of 54 gallons per minute, which is only going to require that 2-inch main. So this 54 gallons per minute is significantly smaller than that 260 gallons per minute. But this 260 was based on fixture flow rates when there are much higher fixture flow rates when this sizing methodology was established. Now our shower flow rates and other fixtures are significantly reduced, and our occupancies are getting up at various times. And so we don't have these peaks like we used to size for. Appendix M is better reflecting that. And once again, you're going to reduce that 4-inch main to 2-inch main, and that will roll over to the roll over into first cost savings, because we all know it's cheaper to buy a 2-inch pipe than a 4-inch pipe, as well as it's going to reduce the temperature maintenance distribution losses, because now our distribution piping got smaller. And so that smaller piping means less heat loss because there's less surface area of that piping. So lots of first cost savings and actually substantial temperature maintenance loss savings as well, which helps us better make use out of those combined systems because it's less of an issue there, and is also appropriate for the dedicated systems as we're reducing that load, which is going to increase the overall efficiency of our system, or our system COP. And we give a lot of these presentations in California, so I'm noting that this is California, or jurisdictional dependent in California, but in Seattle, my understanding is we're all welcome to use this, and it's documented, and there's more information in that 2018 Universal Plumbing Code. So our temperature maintenance system review, first consider the scale of the distribution system and the associated losses. And next we want to drive down those losses through better insulation, better and code compliant thermal clamping supports that are thermal bridge free. And then if we can, utilize the UPC Appendix M for sizing those distribution pipings, more accurately sizing them, more appropriately sizing for these fixtures and the occupancies we see in these buildings. And then understand what type of equipment you're working with and its limitations. Reach out to your manufacturer or your representatives. If you're single pass primary heat pump or a multi-pass primary heat pump, you're going to approach the commercial heat pump water heating system design a little bit differently. So understand what you're working with there. And then dedicated systems using single pass equipment are typically more reliable and higher efficiencies than doing a combined system. And the last point here is we really want to reheat these losses efficiently, because they're losses. This is wasted energy, and it's 10% of the annual building load, or 30% of the annual domestic hot water load. So it's a significant portion of the amount of energy going into these buildings, and it's a loss. So we want to eliminate that loss whenever possible. And pausing for questions there before we talk about system sizing. And I was going to go through an example with the Ecosizer. And so I'm going to fly along here, unless I should be stopping, Lauren.
Just a quick note that I did put the Ecosizer link in the chat while you were gone, so that folks on the line could experiment with that and play with it while you were gone. So
perfect.
Kind of got you covered on that one.
Yeah,
good.
Perfect. That worked out well. Glad it wasn't just a waste of time. So system sizing. The Ecosizer is a great tool that a bunch of engineers at Ecotope and programmers developed to address sizing, because we have our ASHRAE handbooks which help us with the sizing, but most of us are familiar with gas or electric resistance systems that are sized with a very low storage capacity and a very high heat capacity. And so I'm showing that on the left-hand side of this balance here. We have low storage and high heat shown with a lot of flame and a small barrel of water there. Heat pump water heating systems, if you want to result in a lowest first cost, it might be very advantageous to trade off the amount of stored water with the amount of heat capacity you need. And that's what the Ecosizer is really tailored to do, is to help you as the designer understand how you can be sizing these systems to meet the load of the building. And you can do that by trading off between the amount of heat capacity and storage volume. And often with heat pump systems, the storage volume is cheaper than the heat capacity. So we want to prioritize higher storage volumes with lower heat capacity. We also, of course, need to size for the load. And so depending on what load we're sizing for, they look different. A nursing home might have more of a less peakiness in the morning, higher peakiness in the afternoon, early afternoon, compared to a motel or a multifamily residential occupancy, which typically has a higher peak in the morning and then a lower peak in the afternoon. Here's that multifamily domestic hot water use profile, and we can see that morning peak. And then there's also typically an afternoon peak there as well. So our gas water heating systems typically are sized to recover the storage volume in this peak time of use. So there's a lot of heat capacity or recovery rate required to recover in that amount of time, typically a 3 to 4 hour period. I would argue that heat pumps, you're going to make better use out of your money if you're sizing to run for a longer duration and you have a large hot water storage tank or a group of storage tanks to store that water to have a large thermal battery, right? This is essentially trading off how many PV panels you have and how many batteries you have. We can have a very big battery and a very small PV panel and meet a load. We can also have a lot of PV panels and a tiny battery or no battery and meet that load. And it's really more cost effective in the hot water world to increase that battery bank and reduce that PV panel in that example there. So the Ecosizer, it's a free online tool. I have about 6 minutes and I was planning to run through it, so I'll try to do it here quickly. But there's a 8-step list of how to use this tool on the top. There's also some more information in the glossary and documentation that tells you how this tool was built and actually has the open software in there too. But essentially what we're going to define first is the total number of people in our building, the number of apartments in our building, and how much water people use per day. ASHRAE medium is going to assume 49 gallons per person per day, and that's really quite a substantial peak and going to result in higher equipment costs and a bigger system. ASHRAE low is at 20 gallons per person per day and may be appropriate for certain building types, but I would argue that for our multifamily buildings in Seattle, the market rate with low flow fixtures should be, or is about 25 gallons per person per day. And we've at Ecotop studied this across numerous buildings to dial in the range we see here and what that metric is. So I like to do my first sizing analysis for that multifamily building close to 25 per person per day number. Then we also have to define the water temperatures and how hot the water in the primary storage is. So I might say 140 degrees there, and we're supplying out at 120. You notice that when I click on this, we get a little info button that comes up, and this pulls the definition from the glossary. There's also some advanced options, which I won't get into now. And then the last thing, or one of the final things we can select, is the system configuration. And I'll choose the parallel loop tank configuration for this sizing example. Load shift is something that can be super advantageous for these heat pumps, as we're already prioritizing that battery or the size of the thermal storage tanks. Right off the bat, we're trying to have more thermal storage or more battery. That really aligns with load shifting. We can shift more out of the peak time of use pricing periods. So in California, depending on when you use electricity throughout the day, it can be more or less expensive. So this can be used to evaluate how you shift out of those high price periods where electricity is expensive on the grid and only operate that heat pump water heating system when electricity is cheap on the grid, really addressing that operational cost equation. And then the last thing we'll do is click size your system. It's going to do some math in the background and pull up this primary sizing curve. And we just need to be above this green line here, anywhere on this curve. So we can see that the default selection point was based on a 16-hour runtime for that heat pump. And we need 312 gallons of storage and 55 kb2 per hour of heat capacity. We can increase the storage to take that 55 kb2 hour heat capacity down to 45, but now we need close to 400 gallons of storage, and the heat pumps are going to be running for an extended duration or longer than that 16-hour period. We can save these to PDF, log it in our project folder on our company server, and it's going to print you out all this information, which also gives you some guidance on your parallel loop tank, how big of a volume that should be, and the heat capacity required for that. The hot water simulation is also a cool button. I'm just going to point it out to you, and you can explore that on your own.
Colin, just a quick question. How consistent is the peak water usage per person metric?
So the peak water usage per person is what we have done historically, how we've sized historically, and it can vary from building to building. But in general, with our market rate multifamily buildings in Seattle, it's a peak of 25. And so during normal days, most people only use 17 to 18 gallons of hot water. Where we have more family occupancies, they typically use more water. And so we might want to, adjust that 25 gallons per day up a little bit in that case. If you turn on California specification mode, which I did not note, there's some really great guidance in there on the default rates that they assume in California, which may be a place for you to first start with.
And then another, just very quickly, I know you showed load profiles for different building types. Is there anything, do we have any load profiles for like K through 12 buildings?
Yes, so we developed this tool to really address getting these heat pumps into multifamily buildings first. So we prioritize that multifamily building load shape, and that's the only load shape in that sizing tool right now. We are actively working on getting a bunch of other load shapes into this sizing tool so that we can size appropriately for a multifamily building and an elementary school with one program.
Perfect. Thanks, Colin.
So I only got 1 minute left, or maybe I'm out of time now. But after we get our required heat capacity, we can start looking at what products can meet that capacity and what their limitations are regarding the minimum ambient air temperature and the maximum outlet water temperatures. So a really useful graphic that we pulled together for you here that highlights a few of the products available on the market today and some qualities of them. And I'm out of time here, but I'll keep just flying through this. So after we got that we need our 66 or 67 kb2 per hour of heat capacity, we want to select a heat pump based on the design air temperature. So in Seattle, we might be using 20 degrees Fahrenheit. And we know that when 45-degree water is coming in, there's our inlet water temperature. At 20 degrees Fahrenheit, we're going to get 110 kb2 out of this Mitsubishi QAHV heat pump water heater. So that's going to be adequate capacity to meet that load. At more of our normal operating condition, maybe 60 degrees, we're going to be getting a lot more heat capacity out of that device, right? So this chart is meant to highlight that although the manufacturer may be rating their heat capacity at 60 to 70 degrees Fahrenheit, you need to be focused on the design air temperature that that heat pump water heater will be serving. Yeah, so we got a slide here. I'm putting the pieces together to remind us all that, you know, these components, primary heat pump water heaters, the primary storage, the temperature maintenance system, and the control system, they're all there in our gas, our electric resistance, and our commercial and residential heat pump water heating systems. We primarily just want to be focused on how we're addressing this temperature maintenance load in our larger buildings with larger distribution systems, because this is often the Achilles heel for these heat pump water heaters. We have an exit survey here. We'd love if you could take some time to fill it out. And I really appreciate you spending your morning with me or a part of it to learn on heat pump water, or learn about commercial heat pump water heating systems. It's been a pleasure to work in this industry for the past 8 years, because I've seen that these systems can dramatically reduce the energy use associated with that large domestic hot water heating load. And so I hope that all of you are encouraged to use it on your next projects and understand some of the design considerations you should be paying attention to during the design, installation, and commissioning phases.
And Colin, if you'll go forward one more, we can highlight the upcoming trainings. So we have, of course, parts 3 and 4 coming up on November, in a week, November 10th, and then a week later, November 17th. And that will be with engineer Evan Green, talking about, you know, further down the line, once you've done your design considerations, what comes next. So we look forward to have everybody join us then. And again, you can get a copy of this webinar presentation and see the video on the Lighting Design Lab website. Should be posted within the next day or two. So thanks to everyone who's joined us today. We really appreciate it. And we hope to see you back in a week. Thanks so much, Colin.
Thank you.
All right, and we'll sign off this morning. Bye-bye, everybody.
Bye.